Yes, my name is Preben. I'm at NTNU and also at Similar Research Lab here in Oslo. And I'm going to be talking about ways that you can break AI systems using something called adversarial attacks, and some ideas for some solutions that you might want to implement, which is what I'm researching in my PhD. So first, just a bit of housekeeping. I'm going to start off with a brief introduction about how neural networks learn, how they're trained. I'm going to be talking about deep neural nets, which, for if anyone doesn't know, that's the sort of the main AI architecture that you'll find in ChatGPT and the algorithms on TikTok as well. So after that brief summary, I'll go through what adversarial attacks are, how they work, and why they're a problem. Hopefully convince you of that. And then in order to introduce a solution, we first need to talk a bit about how neural nets represent information. You could say how neural nets think, if you want to anthropomorphize a bit. And then I'll introduce what we call the causal neural network model, which is sort of my area of research, and end with some thoughts on the state of the art. All right, so first things first. For the purposes of this talk, I would like you to think about deep neural nets as very powerful pattern recognition machines. They're very good at finding statistical patterns in data. They could be very complicated patterns, such as, for example, the patterns relating the pixel values in an image file to the label that you would like to apply to that image if you're building an image classifier. And I'm going to be talking about images in this talk because they're quite nice and visual, but everything I say is sort of equally applicable to AIs that deal with text or speech or stock prices. Okay, so we're trying to identify patterns between some input X and some output Y. We have a very powerful machine, but because this machine is so powerful, it can spot patterns that are false, patterns that don't generalize. So I have an illustrative example here. If you imagine training an image classifier on the cows in the center there, and you train your AI to say, these are pictures of cows, then the AI will likely pick up on the fact that, okay, all of these, they have like some green grassy stuff in the background. That's probably related to what it means to be a cow. You train this, you get good accuracy, you deploy it, and in production you encounter the image on the right. And it's very likely that your AI is going to fail because that pattern no longer holds. It was a false pattern. All right, that's all well and good. It's a cute example, but it allows you to do some more malicious stuff. It allows you to do what we call adversarial attacks by sort of exploiting these false patterns. An adversarial attack for images consists of you start with the image there on the top right, which is of a panda. You have an AI system that correctly classifies that image as being of a panda. And then you add some noise to it, some carefully crafted noise, just a tiny bit, to produce the image there on the bottom right. Probably from the distance you're sitting, you can't even sort of tell that something has happened. It certainly looks quite similar. It's just a tiny bit of noise. But the AI system that you trained now fails completely to classify this as a panda. It thinks it's a cat in this example with very high confidence. And we think that the reason this happens is because, much like the sort of grass cow example, there are some more complicated patterns in your data as well that aren't as sort of obvious and explainable. They can be to do with sort of fine structures in your pixels, all very complicated stuff. And it means that you can add noise in just the right way to trip up the AI. So that's what an adversarial attack is. And it's obviously not that big of a deal if you're just classifying pandas. But, if this was your self-driving car, or if this was supposed to diagnose, like, cancer tumors or something, then it's a bit of a problem. It's very interesting to note that although AIs are very susceptible to this type of attack, humans are basically immune. Like, hopefully no one in this room looks at the bottom picture and thinks it's a cat, right? All humans sort of naturally are able to defend against these attacks. And the hypothesis is that the reason humans are very good at this is because we are naturally good at extracting what we call the causal information in this case, an image. And that means we're good at extracting basically the important information, the information that affects, in this case, the classification we're trying to make. And we're not fooled by sort of random noise in the background, the way that these statistical pattern machines are. And there is a theoretical solution to this vulnerability, and it is, if you're trying to recognize pandas, you just need to collect all images possible of a panda. You need to go out with your camera and take pictures with all types of backgrounds, all types of lighting conditions, and camera angles and lenses and all that kind of stuff. That's obviously kind of impractical. So we would like a solution that we can do without having to leave the office. So to introduce sort of why or how we can go about solving this, we first need to dig a little bit deeper into how neural nets think, how they represent the information that you give to them. So I've drawn a very simplified schematic here of a neural network, in this case processing images. So this could be the panda classifier. And we see that a neural net consists of a bunch of layers, and they process the information you give it sequentially, starting with the first layer and then moving up to the second and so forth. So the first layer here looks literally at the RGB channel values of every pixel. So that's a lot of information. You can have 200 by 200 pixels in an image with 3 color channels. That's 120,000, I think. But that's very low level information. That's raw pixel data. Then there happens a bunch of processing, and the information is fed to the next layer, which is smaller. So this next layer has a smaller capacity for sort of storing information, and it needs to sort of disregard the low-level details and then try and sort of extract some more high-level stuff. So the next layer might sort of learn to identify basic lines and corners maybe in your image, do some like very basic processing. And then you sort of move down the chain here to deeper and deeper layers. And at every stage, the information is compressed down to a more sort of abstract, high-level representation. So at the very end, you might have quite a small layer that encodes information about, I don't know, like faces and sort of fur and snouts or whatever for your animal classification. And then at the very end, a prediction is made based on that sort of compressed information. So you can basically think about this as a lossy compression algorithm aimed at sort of extracting a particular type of information. Okay, so this allows us to sort of reduce down from all the possible combinations of pixels to a smaller combination of sort of high-level codes or compressed representations of the same information. Right. We now have all the pieces we need to think about what we call the causal neural network architecture. And instead of having a single processing pipeline, like we saw in the previous example, the causal neural net takes in the image and then produces two independent sort of information streams. Label 1C here for content, the content of the image, such as subject and shape. And there's one called S for all the other information, the lighting, the camera angle, call it the style information. So this is an architecture which aims to separate out all that important information to put it in the C stream and leave all the unimportant stuff, all the style information, all the like grass information in the S stream. And if you're able to do this sort of correctly or sufficiently accurately, then you can do something quite clever, which is that you can introduce, there's a little box here that says perturb signal. What that means is you take in your style signal and you jiggle it around. You add some noise to it. You flip a few bits here and there just to try and corrupt it a bit. Make some variations on the original style signal. So you might, produce sort of, say, 10 different variations on the actual style signal that was in the image. And then you sort of one by one recombine these with your content stream, and you have your neural net make a prediction at the end. And very crucially, you tell your neural net that regardless of what I do to the style signal, you should always predict the same label. So this sort of allows you to approximate that gathering of all possible images in a much more manageable format, and under certain quite lax mathematical conditions that I'm not going to go into, this sort of converges to a system that is able to do what humans do, to sort of extract the causal important information. So this causal neural net architecture is quite a new thing. I think the first papers I saw discussing it are from like 5-ish years ago, maybe, and they've gained a lot in popularity over the years since, because they are, as we've talked about, not fooled as easily by adversarial attacks. They're not fooled by sort of adding noise to images, or if you're doing text, they're not as easily fooled by swapping words and sentences. But we still have a long way to go, even though they have all these sort of desirable properties. So that's what I'm doing in my PhD. I got 3 years left, so I'm sort of trying to make some progress on these things. There's a lot of interesting stuff that goes into that green box. That's a separation mechanism that tries to separate these information streams. That's highly non-trivial to design. There's also a question of how you know that the C and the S signal streams, that they contain the information that you expect them to contain. And how do you? We've talked in very qualitative terms here. How do you make this sort of mathematically rigorous? So a bunch of open questions, but they have shown a great deal of promise. They're good at adversarial attacks. They're good at generalizing, doing stuff like training on one data set, testing on another data set, those types of tasks. And I'm quite a fan of them, as you might have guessed. Otherwise, I wouldn't have spent 4 years of my life sort of researching them. But so hopefully that sort of piqued your interest in how these can be used to make more secure AI systems. Thank you.
All right, this was a short talk, but we finished early. So, anybody have any questions? All right, let's go.
Hi. I remember reading a tweet from some cool guy in neural network some time ago. I think it was Jan LeCun, but I'm not sure.
Yeah, he tweets a lot.
Huh?
He tweets a lot.
Yeah, probably. So basically what he said is that any attempt to make your neural network smarter, but trying to explain it how to think is is bound to fail. Eventually, the bigger neural network with more data will win. So it's a failing strategy. So what do you think about that? And also another question is, when you showed the first adversarial attack with some crafted noise, my first, what I thought was maybe it's about how we access this data, humans, that, for us it's a little bit blurry. We don't get access to the individual values of those pixels. So why not just make the image a little bit blurrier with some random noise? In other words, just put your perturbation step as the first step, and that's it. Why doesn't that work? Thanks.
Yeah. Okay, so to answer the first question first, which is, can't you just solve this with sort of more data? The answer is yes, eventually. If you have sort of infinite images, you're guaranteed to get a robust or a secure neural net. But I think the question is more about how quickly you can get to that step. Because if it requires it's very possible that it requires more images than humanity will ever produce in its lifetime, and then it's sort of unattainable. So I think the causal neural net architecture enforces sort of some guidelines on how you'd like the information to be processed to use that data more efficiently. Because with perturbing your style, you can basically turn one image into 10 or 100. So it allows you to sort of extend the data that you have. And I also want to say that Jan LeCun has published a full manifesto about how you should make AIs think. So, who is he to talk? To answer your second question about why don't you put the perturbation step as your first step, that's a good idea. It's an established strategy, which we call adversarial training, and it basically means you do this to your training set and then you train. The issue with that is that it sort of makes you good at defending against a specific type of attack. It makes you good at defending against the attack you trained against. But there are sort of many different attack algorithms, and you need to patch each one. And if someone uses a different one that you haven't trained on, then you're a bit screwed. So that's a practical solution for sort of patching problems, but it doesn't solve the underlying issue.